All right, so after our last video on average value, we're going to see how this is applied to something called the mean value theorem for integrals. So take a second, pause the video and read this before I start explaining just so you can get an idea of what it is. All right, so if you've read through this, hopefully you'll just see that really this is no different than the original mean value theorem for derivatives that we discussed back in the first semester, which was that if we have a differentiable function over an interval a to b, then there has to be at least some value, which we will call c, that is between a and b, where the instantaneous rate of change of that function is equal to the average rate of change over that interval. And this is no different, except instead of using the word rate of change, we just use the word value. So for instance, this basically just says there has to be some place, if we have a differentiable function on the interval a to b, that we have some value c that's between those values a and b, where the function takes on its average value. So in this situation down here, we can see that the average value of the function is this dotted line right here. And in this case, we have 1, 2, 3 places where the function will take on its average value over this particular interval. So really that's just about as much as it is. It's really just using one application of the average value formula, which isn't too difficult, especially if you've gotten accustomed to looking at the mean value theorem as we did apply to derivatives in the first semester. But what I want to show you is that if we apply the mean value theorem to integrals on a rate of change function, we actually get the mean value theorem for derivatives. And I'll show us this in this next slide. So, for example, if we're looking right here at this first one, this is saying, okay, there has to be some point C where the instantaneous value of the rate of change is equal to the average value of the rate of change over the interval a to b. Remember that this is the average value equation. The function we have inside the integral is f prime. So if we take that integral and divide it by the interval, we get the average value of f prime. Okay, well again, remember that if we evaluate this integral right here, this just gives us, and I'm going to try to write this with the mouse, so this might be a little bit entertaining. This is just going to give us f of b minus f of a, or the net change in f of x, and that looks just like something that would have been on my household refrigerator when I was 5. But anyway, okay, you guys get what I'm trying to say. So basically, this is another way we keep this left side the same. When we evaluate the right side, don't you see that all we get is a mean value theorem for derivatives? This is just saying there's one point C where the instantaneous rate of change is equal to the average rate of change over that interval. Well, there's no different than saying there is one point C where the average value of the rate of change is equal to the average value of the rate of change, as given by this integral expression. So just wanted to show you that slide, just so you saw that they were the same. And actually, I didn't catch this when I was creating this. Just realized I forgot to put a G out in front of there, but it's okay. Still works, because that's another way of saying, because that's what we do in this class. We remove the G's from the active verbs, or whatever they're called. Whatever. This is an English class. Thomas Watts, where are you to correct me on my grammar when I need you? All right, anyway, so now that you guys got this, try to see if you can find the values which satisfy the mean value theorem for this function over this interval. And what I want you to try is, just to refresh on the mean value theorem for derivatives, I want you guys to look at applying the mean value theorem to the derivative of this function to find where the average rate of change is equal to the instantaneous rate of change, but also apply it using the integral mean value theorem, which we just discussed, where we find where, at what points, this function takes on its average value. All right, so if you're giving this a try, if we try to do the first way, which related to derivatives, first we got to calculate the derivative of this function, which would just be this right here. And then what we want to do is we want to set some value of c evaluated at that derivative to be equal to the average rate of change of that function. So when I do this, I got these two c values. If we go down here and look at a graph, we can see here is the instantaneous rate of change function in green. Here's the average rate of change, and these are the two x locations where that instantaneous rate of change equals the average rate of change. So this was solving, again, the mean value theorem as we apply it to derivatives. So you guys could have done this problem in the first semester. But so now let's take a look at how we would solve this thing using second semester methods. So try to do it with the mean value theorem for integrals. All right, so if you tried this one, you'd see what we got to do is, in this case, we are setting the instantaneous value of the function, where in this case we don't have to have a derivative because we're just looking at the value of the function, is equal to the average value of that function. And again, this is a derivative we can calculate using fni and t. Down here in this plot, if we do calculate that derivative, or that integral, you should get the value 2.14. Remember, 2.14 is the value of that integral divided by 1 over 3 minus 1, or 1 over 2. So if you're not getting that exact same value, don't forget to put that in front of the integral. So anyway, that 2.14 is in fact the average value of this particular function over that integral 1 to 3. And if we plot our function and we plot what the average value is, we see, and I didn't highlight this one, but this value, this intersection, is right at about 2.92. So if you weren't able to get these problems, just go back over the video, try to give them another shot. But that's pretty much it. That's average value and the mean value theorem applied to integrals. Not too difficult. However, if you do have questions, please come into class and ask those, and hopefully we can clear those up.